The molecules that we've looked at so far didn't have any lone pairs on the central atom, but lots of atom molecules do. So now we need to talk about two different types of geometry, electron geometry and molecular geometry. The electron geometry is the arrangement of the electron groups, and you always have to look at that first. The molecular geometry describes the positions, the arrangement of the atoms. If you have no lone pairs, those are the same thing. If you have lone pairs, then they're going to be a little bit different. So let's consider ammonia. Let's just have its Lewis structure here. So the Lewis structure has 4 electron groups, a lone pair and 3 single bonds. Okay, that's 4 groups. 4 groups makes a tetrahedron. So those would spread out into a tetrahedron like this. That's the electron geometry, the shape of the electron groups. But this is a lone pair. It's not an atom up here. So the molecular geometry is just looking at where the atoms are. Because remember, electrons are incredibly small compared to incredibly small atoms, right? So these lone pairs, way, way smaller than an atom. So what I like to do is I like to think of those as being invisible balloons. So if that was an invisible balloon, make it disappear. I'm not popping it. It's not going away. It's still there. It's just invisible. Maybe it's like a clear balloon. You can see straight through it. The molecular geometry is describing the shape of where the atoms are. So you make that lone pair invisible, and then you describe this shape. Well, this is a triangle, right? So this would be, actually that's the wrong color ball. So this would be the 4 electron groups, right? They're making that tetrahedron. Now we make the lone pair invisible, and we describe that shape. You look at it from the top, it's a triangle, but is it in a plane? Is it flat? No, it isn't. It's making it like a short little pyramid, right? So this is called trigonal pyramidal. It's a trigonal pyramid. The base is a triangle, and it comes up to a point in the middle. It's not, like a real steep pyramid like the Egyptian pyramids, but it is a pyramid. Any questions? You have to look at the electron geometry first. Because if you just look at the atoms and say, oh, well, there's 3 atoms, you would say that it's trigonal planar, that it's flat. But that lone pair is definitely there. It is repulsive. It's actually more repulsive than the atoms and the single bonds. So why is it more repulsive? Well, if we think about a bonding pair of electrons, those are going to be trapped, stuck, confined between 2 nuclei. Whereas a lone pair is attached to, or, getting close to the nucleus here, but then over here it's not constrained by anything. It just kind of spreads out and gets all puffy, right? So this is taking up more space than this one. So with our ammonia molecule, this lone pair, you could think of that as being, it's really more like this shape. It's big and fat, right? And so that's more repulsive than these single bonds. And so what happens is that, just like the double bond in formaldehyde, that is going to push these guys together a little bit. So in ammonia, that angle becomes 107 degrees. A perfect tetrahedron would be 109.5. I do not expect you to remember the number 107. You should be able to tell me that that angle is less than 109.5. because they're being crowded a little bit together because collectively they hate the lone pair more than they hate each other. Okay? This is a lovely lecture about hate. Let's look at water. Lewis structure for water. So we have, wrong pen, oxygen and 2 hydrogens. And typically we draw it like that. Not exactly sure why, but. So we have 2 lone pairs on the oxygen. So if we're looking at shapes, we first look at number of electron groups. How many groups? 4. What do 4 balloons make? A tetrahedron. So we've got a tetrahedron electron geometry. The electron groups make a tetrahedron. To do the molecular geometry, we're going to make these lone pairs invisible. Bye-bye. Bye-bye. So those guys are gone, giving us this shape. And that one has the very fancy name, bent, because it's not straight, right? It's just bent. So some of these names sound all fancy, like trigonal bipyramidal, right? You impress your friends if you can say that. And this one, it's bent. It's kind of a letdown, but it's bent. So if we look at the bond angle here, again, the electron groups start out as an ideal tetrahedron, so 109.5, but then when we recognize that 2 of these are lone pairs that are more repulsive, these hydrogens are going to be closer together even than the nitrogen, than the hydrogens on the ammonia with only 1 lone pair. So this is going to be 104.5, but again, what you need to be able to tell me is that it's less than 109.5, which is the perfect tetrahedron angle. Any questions? So this is relative repulsion of electron groups. So 2 lone pairs would have the biggest repulsion for each other. A lone pair and a bonding pair would be the next greatest repulsion, and 2 bonding pairs would have the least amount of repulsion. So on water here, the repulsion between these bonding pairs is less than between the lone pairs, or even than between the lone pair and the single bonds. What is the molecular geometry of a molecule whose central atom has 3 bonding groups and 1 lone pair? This requires a picture, either in your head or actually drawn on something. We have a molecule whose central atom has 3 bonding groups, so 3 bonds. It doesn't say what kind, doesn't matter, and 1 lone pair. We need to know how many electron groups are there. There's 4, right? What do 4 balloons make? A tetrahedron. Okay, so we have a tetrahedron, but what about that lone pair? That's an invisible balloon. Okay, so if we draw this tetrahedron. There's the 4 things, right? But one of these is a lone pair. So we have 4 groups. One's a lone pair. Electron geometry is tetrahedral. When we're talking about the molecular geometry, we're going to make that lone pair invisible, without moving anything else. Triangle pyramid, or trigonal pyramid. So, these words are intended to be descriptive, okay? You just have to become a little bit familiar with them. So, trigonal, this is a triangle thing. Tri means 3, right? Tetra means 4. That's a line. Plane Planar is in a plane, it's flat. Pyramid is not flat, sticks up in the middle. So this is a trigonal pyramid. I circled that with white, could you tell? Any questions? Okay, what about 5 electron groups with lone pairs? So if we look at SF4, so there's 4 fluorines attached to the sulfur, and we count up all the valence electrons, and we distribute them around, and what we'll find is that after we've given everyone an octet, we have 1 more pair of electrons. And I don't know where those guys came from. Go away, go away. So what sorts of atoms can expand their octets, can have more than 8 electrons? Period 3 and larger things, right? So fluorine is in period 2, can't do an expanded octet, he's too little. Sulfur's in period 3. Sulfur can do an expanded octet. So we can take that extra pair of electrons and make it a lone pair on the central atom. When you're drawing your Lewis structures, all of your electrons should be paired up, except in the very unusual situation where you're drawing a free radical, then you'll have 1 unpaired electron. But we almost never do that in Chem 1A. So, some of you are doing your Lewis structures like this, and you got electrons floating all over the place. Don't do that. They're all going to be in pairs. So they're bonding as a pair, or they're alone as a pair. Stupid. Keep touching the screen and more electrons appear. Okay, so how many groups on the central atom? 5. So 5 makes that bipyramid shape, trigonal bipyramid. That trigonal bipyramid has axial positions and equatorial positions. The angles are different. We're not going to put this lone pair in an axial position because here it has a 90-degree angle with 3 other electron groups. If it takes an equatorial position, it has a 90-degree angle with only 2 electron groups and 120-degree angles with the other ones. So it has more space over here. Okay? So that would be like this one. Okay? So if one of these is a lone pair, it's going to be one along the equator. And so, if I tip this, it's not the same, right? There's the up and down, there's 2 that are directly across from each other, and then there's the ones in the middle that make a triangle. So this is the one that's going to take the lone pair because there's more space. So then when we make that invisible, what shape is that? Look at this. Teeter, totter, bread and water, bread. It's a teeter-totter, a seesaw. So another fancy name, the molecular geometry is seesaw. Okay, any questions? BRF3, here the Lewis structure is drawn for us. Also 5 electron groups, right? So the electron geometry is that trigonal bipyramid. But we're always going to put the lone pairs around the equator because there's more space there. So the second lone pair goes along the equator. Oh, there's my teeter-totter. So the second lone pair is also along the equator, and I make that one invisible, and that's a T. It makes a T shape. Okay? So yet another fancy name, T-shaped. XEF2, look at this one, like this. So 5 groups again, trigonal bipyramid, 3 lone pairs. The lone pairs are going to go around the equator. So I have 1 equatorial position left. I'm going to make that a lone pair as well. And now I'm left with 3 atoms in a line. It's linear. There's somebody at my door. Any questions? Okay, 6 electron groups with lone pairs. Here's BRF5. 6 electron groups, so we get the octahedral geometry. All of the angles are the same in the octahedron, so it doesn't matter where we put it, it's all equivalent, but there's going to be a lone pair on here. So here with my models, I've got an octahedron. In the octahedron, I can make this pair axial, or I can tip it around and make that pair axial, or this pair axial. It's just all equivalent. So I'm going to take one of those and make it a lone pair. So there it is without an atom. And then to talk about the molecular geometry, I'm going to make that invisible. And we need to describe this shape. Well, that is a square pyramid. So it has a square at the bottom, right? And it goes up to a pyramid, a square pyramid, or a square pyramidal. If we have two lone pairs, we still have 6 electron groups, so we get that electron geometry that's octahedral. Here's that first lone pair, and now when we put the second lone pair in, we want to maximize the space, minimize the repulsion, and so lone pairs and lone pairs hate each other more than single bonds hate lone pairs. So this other lone pair is going to go on the other side, right, like this. So they're going to be opposite of each other so that they can have a 180-degree angle between them. And so then we describe what's left, and this is a square, right? And it's flat. So this is square planar. That's a square. Any questions? This is table 11.1 from your textbook, which summarizes all of this. So you can look at this, it's by electron groups, and then number of bonding groups, number of lone pairs, the name of the electron geometry, the name of the molecular geometry, approximate bond angles, and examples. What I recommend as you try to assign shapes or geometries is that you do it without looking at that and use this to check yourself. Let's look at this hypothetical question. Imagine that a molecule with 6 electron groups is confined to 2 dimensions. This is not how real molecules are. This is a made-up molecule. So it's flat in the screen, right? So it has a hexagonal planar geometry. So it's flat just like it looks. 2 of the 6 groups are lone pairs. Where are they located? So the choices here, 1 and 2, 1 and 3, 1 and 4. So this is one of the lone pairs. Where's the other lone pair going to go? It's going to go directly opposite so that they can get far away from each other. Does that make sense? So the answer would be C. This is a summary of VSEPR theory. Which statement is always true? These are always, tricky. Always and never. You gotta be careful. Well, let's see what is different here. It's the shape of a molecule is determined by repulsions among bonding electron groups among non-bonding electron groups determined by the polarity of its bonds, or determined by repulsions among all electron groups. Which one is true? Is it just the bonding groups that affect the geometry? No. Is it just the non-bonding groups, the lone pairs? No. They both have an effect, right? So it's this one, all the electron groups, bonding and non-bonding. So this is true. The polarity of the bonds does not affect the shape of the molecule.